we'll start with a brief overview of PMC. Next, we'll list pain points that are specific to energy efficiency and PMC's solution that addresses those pain points. Then we'll dive into the details of our solution. Finally, before we take questions, we'll wrap it all up with a demo follow-up and a couple other topics. Before we dive into today's topics, I'd like to share a brief introduction to PMC. Since 1979, PMC has helped over 700 companies by completing more than 7,000 performance-enhancing initiatives worldwide. Our commitment to excellence has brought us to the point where we are the largest independent industrial engineering services firm in North America. Our next topic is an overview of energy efficiency optimization. Energy optimization has several pain points, including the U.S. Energy Information Administration predicts a 56% rise in energy consumption between 2010 and 2040. The industrial sector accounts for over half of global delivered energy. Growth is predicted globally, but it's greatest in non-organization of economic cooperation and development countries like China and India. Obviously, this puts a lot of pressure on utilities to increase their capacity and on industry in the form of rising costs. Similarly, rising energy costs are predicted. This chart shows the cost predictions for natural gas, which is becoming an increasingly popular source for electrical generation. The terms green along with sustainability are becoming more and more popular. More companies are incorporating green initiatives, and more consumers are becoming aware of the importance of green products and services. Green certifications are becoming more popular, and so are the number of consumers who make purchase decisions based on these certifications, as well as organizations and governments that require the purchase of environmentally preferable products and services. The Green Seal has been around since 1989. Their standards cover over 375 product and service categories. Energy Star is an international standard for energy efficient products, appliances, and buildings originated in the USA. It was created in 1992 by the Environmental Protection Agency and the Department of Energy. Other countries like the European Union, Australia, and Japan have also adopted the program. Unlike other certifications that are primarily known for products, the U.S. Green Building Council is a non-governmental organization that promotes sustainable buildings and cities. They developed the Leadership in Energy and Environmental Design, or LEED, third-party green building rating system that includes 4 levels of certification: certified, silver, gold, or platinum. At least 18 other nations have similar councils. In Europe, the Eco label was established in 1992. It considers the whole life cycle of a product from extraction of raw materials through manufacture, packaging, distribution, use, and disposal of the product. Companies are reviewed every 3 to 5 years to keep up with innovations. Other green certifications are available in other countries like Environmental Choice in Australia. So you can see that green certifications are becoming more and more important worldwide. Finally, green regulations and mandates are increasing. In the United States, the Environmental Protection Agency, or EPA for short, writes and enforces environmental regulations. Their enforcement powers include fines, sanctions, and other measures. Their primary focus has been on environmental pollution, including air, water, and hazardous waste, as well as fuel economy and automobiles. But they also launched the voluntary Energy Star program that we just mentioned. The Regional Greenhouse Gas Initiative, or RGGI for short, is a regional initiative by states and provinces in the Northeast United States and Eastern Canada to reduce greenhouse gas emissions. They are designing a cap and trade program for greenhouse gas emissions from power plants, so states and provinces can benefit by minimizing energy consumption. The solution to these problems is two ingredients. First, dynamic simulation modeling of systems using a tool such as Siemens Tecnomatix Plant Simulation software provides a powerful virtual environment to test and improve a system's design and operations to address traditional optimization issues such as maximizing throughput, minimizing inventory and buffers, and minimizing labor. Among the numerous simulation products that I've used, Plant Simulation also happens to be my personal favorite tool due to its unique, powerful features. Second, while Plant Simulation's always provided a powerful engine to build, analyze, and optimize your processes, the new energy features that were added to Plant Sim's recent version now let you simulate energy consumption and analyze and optimize energy efficiency. Our next topic covers the details of our plant simulation energy solution. The first reason to incorporate energy optimizations is to reduce energy consumption, which translates to reduce cost for you. In other words, you can increase your profit margins. Optimizing energy efficiency can also result in reduced failures and maintenance needs. Energy optimization can also help you to achieve green certifications like the U.S. Green Building Council LEED certifications and to meet regulations and mandates. This can help to raise the reputation of your company with your customers and help you to qualify for possible tax rebates and zoning allowances. Additionally, since energy optimization features are seamlessly incorporated in PlantSim's traditional throughput simulation features, you automatically have a simulation that you can use to play what-if games to increase throughput, minimize labor, minimize inventory, or optimize scheduling. The new Energy tab appears with the other input and output tabs and several objects that PlantSim provides to model stations, machines, conveyors, etc. This lets you model the dynamic energy management available in modern control units like Siemens S7300 using the Profit Energy protocol without any custom programming. So you can easily experiment with energy what-if scenarios in a virtual environment. The left side lets you specify the power input in kilowatts required for a station's various states, like when it is setting up, working, failed or down, or standby. The right side lets you specify the transition times between energy states, like operational to standby. The state transition button even lets you model the saving of energy, specifying energy state transitions for pauses or breaks within shifts, or when a new shift starts after an off-shift unplanned period. You can even choose to power up early so that the machine is fully operational immediately after breaks or when a new shift starts after an off-shift period. This lets you save energy without decreasing throughput one bit. The Energy Analyzer Object's Show Visualization option lets you quickly pinpoint areas of high energy use. Stations and conveyors with the highest energy consumption are surrounded by a solid red circle. Open red circles have slightly less consumption. Purple circles are intermediate consumption, and blue circles are the lowest consumption. The Energy Analyzer Object's Display Panel option displays overall energy statistics for the whole simulation, including total energy consumption in kilowatt hours and total energy consumption while in the operational or waiting state, as well as the current power in kilowatts and the maximum power. The energy analyzer object's diagram of the energy consumption option displays a graph that shows the kilowatt hours that each station consumed while in various states like working, operational, and standby. And the standard resources statistics time and state chart has a new powering up and down state added to include that energy option. The energy analyzer object's table of all evaluated objects option displays a table that shows the total kilowatt hours and kilowatt hours consumed while in different states like working, operational, and standby for all individual stations. The energy statistics button on the statistics tab of an individual station object shows the total consumption in kilowatt hours and the portion of consumption in different states like working, operational, standby, and off. PlantSim standard tools can also help to analyze and optimize your process, including the experiment manager that can automate the running of what-if scenarios. The bottleneck analyzer can help you pinpoint bottlenecks quickly. And the Sankey diagram lets you visualize the flow. The thicker the line, the greater the flow. And now, the moment you've been waiting for, it's time to show the full video of an energy simulation of an LCD TV flat screen production facility. Hello, welcome to PMC's Tecnomatix Plant Simulation Energy Efficiency Optimization demo of an LCD TV flat screen assembly plant. We'll start with a screen tour of our plant simulation model. The source puts skids on the conveyor to the right, which moves skids up to the main assembly line. The main board is placed on the skid at station A1. The display panel is added at station AS3. The power supply is added at station AS5. 3D stereo visualization is added at station AS6. The sound device is added at station AS7. The frame is added at station AS14. The casing is added at station AS15. And then the panel goes through quality, localize, inspection, packaging, and labeling processes before being removed from the skid and transferred to the finished product drain where throughput statistics are collected and displayed. As you can see in our shift calendar, we are running a 9.5-hour shift from 8 a.m. to 5:15 p.m. with a 15-minute pause or break at 9 o'clock, a 45-minute lunch break at 11:30, and another 15-minute break at 2 o'clock. Using Plant Simulation's powerful traditional modeling and analysis tools, the existing model was optimized for a maximum throughput of 1,976 screens per day. What-if experiments also showed that a minimum of 80 skids was required to maintain that throughput. Since Plant Simulation now can model, analyze, and optimize energy consumption, we set new goals for our plant to reduce energy consumption without decreasing throughput. The first step is to specify power inputs in kilowatts in the energy tab of the stations for all its states, including working, setting up, operational, failed, standby, and off. We also specify the transition times between states. Similarly, we specify power inputs and transition times in the energy tab of the conveyors. Now we'll run the model for one simulated day. We'll run the model slow for a while so you can see everything in action, starting with the first skid being placed on the main line and throughput statistics being collected when the screens are removed from the skids after the packaging line. After one day of simulated time, you can see that our throughput is the optimized value of 1,976 screens that was mentioned before. Since we added energy inputs for our stations and conveyors, the Energy Analyzer's display panel also provides valuable overall statistics, including 1,899.7 total kilowatt hours of energy consumed. Let's take a look at the Energy Analyzer's Show Visualization option. The stations surrounded by solid red circles are the ones that consume the most energy. Hollow red circles indicate the next largest energy consumers. Blue indicates the least energy consumers, and purple is in between. This visualization lets you quickly identify areas where you may want to focus on making potential individual energy improvements. This is similar to using PlantSim's bottleneck analyzer to help you to identify the main throughput bottlenecks. Instead of diving into individual station details, let's take a look at the Energy Analyzer's Show Plotter option. This shows kilowatt consumption at any given time. As you can see, from midnight until the start of the one shift we are working at 8 o'clock in the morning, all the stations and conveyors were in operational or waiting state and consumed approximately 77 kilowatts. Then at 8 o'clock, the equipment switched to working state and consumed about 85 kilowatts. During the 15-minute break at 9 o'clock, equipment switched back to operational, then back to working state until lunchtime. During the 45-minute lunch break, the equipment switched back to operational. After lunch, we're back to working state. At 2 o'clock p.m., we're on a 15-minute break, so we're back to operational. Then back to work after the last break of the day, then back to operational state from the end of the shift at 5:15 p.m. until the end of the day, since we are only working one shift. After looking at this chart, you may have guessed that we could save energy by switching to standby during breaks instead of leaving everything in the operational state. The great thing about plant simulation is that this can be tried out as a what-if experiment. To do that in our model, all you have to do is check the on-screen Save Energy Standby During Breaks checkbox. Now, after running our model for one day, our Energy Analyzer's display panel shows that we've decreased total power consumption from 1,899.7 kilowatt hours to 1,820.9 kilowatt hours. This would result in a nice decrease in your energy bill over the years. Also, we achieved these savings without any decrease in throughput. Let's take another look at the Energy Analyzer Show Plotter option. Instead of being in the operational state consuming about 77 kilowatts during breaks, our equipment is now in standby state instead, consuming only about 14 kilowatts. After looking at this chart, you may have guessed that we could save even more energy by switching to the off state during off shift or unplanned time, instead of leaving everything in the operational state. Since these periods are long, we are switching to off state instead of standby for even more energy savings. To do that in our model, all you have to do is check the on-screen Save Energy Off During Night checkbox. Now, after running our model for one day, our Energy Analyzer's display panel shows that we've decreased total power consumption from 1,820.9 kilowatt hours to 819.1 kilowatt hours. This would result in dramatic savings on your energy bill. And once again, we achieved these savings without any decrease in throughput. Let's take another look at the Energy Analyzer's Show Plotter option. As you can see, during off shift or unplanned time, instead of consuming approximately 77 kilowatts, our equipment is consuming just about 8 kilowatts. And during breaks, instead of consuming approximately 77 kilowatts, our equipment is consuming about 14 kilowatts. The secret behind modeling these energy saving measures is the State Transitions button on the Energy tab for our station and conveyor objects. The left side tells PlantSim what to do at the start and end of a pause or break within a shift. Here, standby is specified. The right side tells PlantSim what to do at the start and end of unplanned or off shift time between shifts. Here, off state is specified. And last but not least, the power up early option lets you power up equipment early so that your equipment is ready and raring to go as soon as working time pops up. So you get no decrease in throughput. Now, if we look at the energy analyzer's show visualization option, we can see things have improved, but power supply stations 1 and 2 are still high energy consumers, as indicated by the solid red circles. If we look at the energy analyzer's show chart option, you can see that the power supply area consumes a lot of energy while in the operational state. We can see the details by highlighting the area in the chart. The light green areas for power supply stations 1 and 2 show that these stations consume a lot more energy in the operation or wait state than the other stations. While running the simulation, it appears that the power supply buffer is always full. A look at the buffers chart shows that it's almost always full with 150 power supplies. Every time a power supply leaves the buffer for the main line, the power supply line puts in one more unit, hence the near straight but jagged line. One potential energy optimization opportunity in this area would be to treat this buffer as a Kanban buffer, where the power supply line feeds the buffer only after it reaches a lower level of contents. In our model, the Save Energy Power Supply checkbox sets the power supply line up so that the buffer is filled at the start of the simulation, and thereafter it's fed only after 50 units are left in the buffer. Now, after running our model for one day, our energy analyzer's display panel shows that we've decreased total power consumption from 819.1 kilowatt hours to 755.9 kilowatt hours. And once again, we achieve these savings without any decrease in throughput. Finally, if we take another look at the energy analyzer's show visualization option, we can see things have improved dramatically in the power supply area. Instead of solid red circles indicating high energy consumption, power supply stations 1 and 2 are now purple, indicating a medium level. There is room for even more optimizations, but I hope you've seen enough to see how useful Plant Simulation's new energy optimization features can be. Before we end this video, let's review what we've accomplished. First, before this video, throughput and skids were optimized using Plant Simulation's traditional modeling analysis and optimization tools. Then, using PlantSim's new energy features, energy consumption for one day's production was reduced from 1,899.7 to 755.9 kilowatt hours. This was accomplished with no decrease in throughput. Finally, no new equipment or costs were required, just changes in control logic. To recap, the optimizations shown in the demo model, throughput had already been optimized using PlantSim's traditional modeling analysis and optimization tools. Number of skids had already been optimized too. Then, using PlantSim's new energy features, energy consumption for one day's production was reduced from 1,899.7 kilowatt hours to 755.9 kilowatt hours. This was accomplished with no decrease in throughput. Finally, no new equipment or costs were required, just changes in control logic. You've seen the benefits of modeling energy consumption. This slide shows the average return on investment experienced by 600 plant simulation users in a wide variety of industries who perform traditional discrete event simulation analysis and optimization that did not include the modeling of energy consumption. The results include a 12-to-1 average value cost ratio. I've witnessed this kind of return on investment in projects that I've been involved in. As you can see, Plant Simulation's open architecture allows it to interface with nearly any other software product, including databases, spreadsheets, factory CAD, even PLCs on the factory floor. If you currently use or plan to use Team Center, then you'll be able to share any PLM data that resides there while maintaining the advantage of keeping current data in one place. We'd like to mention that other libraries are also available for PlantSim that add special functionality to the powerful base features of plant simulation. The Warehousing and Logistics library provides numerous objects that slash the time required to build, analyze, and optimize a warehouse model. Visualization includes informative 2D icons and realistic 3D icons. The Value Stream Mapping library lets you build, visualize, and analyze your process in value stream mapping format. The Food and Beverage library provides numerous objects that slash the time required to build a food and beverage simulation model. Visualization includes informative icons that show the state of an object, like how full a tank is. Other libraries are also available that provide specialized tools.